Thank you, everyone. So, as you can see, I had a little bit more hair previously. So, I'm senior data scientist at EPAM, and I actually have quite a curvy road to data science. So, I first studied linguistics and Swedish language. Then I had my master degrees in cognitive sciences, but now I end up in EPAM working like data scientist on NLP tasks. And today our talk is dedicated to some of our use case studies, which we had. So this project we had for one of our customers. And this is actually going to be quite a technical talk because I will describe several techniques that we used for solving the problem. I will describe in details our solution in terms of neural network architecture, but I will start from task formulation, what we actually had to do in terms of data science, what business requirements we had. Then I will move to metrics that we used. Again, then I will describe my technical solution, some custom techniques, heuristics, and then we will end up with results. So our customer, I actually cannot name the name of a company, I cannot disclose it, but it's a major financial analytic organization, which inside the infrastructure has a service which is called Data Lake. Data Lake is some kind of a database which consists of a bunch of texts which are about business topic or some finances. Those texts can be like some financial reports, they can be some transcriptions of business meetings, etc., etc. And by nature of this database, all the texts there, they don't have like free access. And if some user from inside the company wants to access any text, he or she should ask for access to the owner. So the user should apply for this access. And only if the access is granted, only then user can like read the whole text. But we decided to develop a feature which will give a user like understanding insight if the text is actually worth reading. Because if you have only name of a text, you don't understand that if it's worth reading for you actually. So in terms of a data science, this can be formulated as summarization task. Okay. And summarization task in a nutshell, it is we just need to create some new text which best represents the content of original text and gives the most like relevant information from the original text. And in text summarization, there are mainly two approaches, extractive and abstractive. Extractive approach is when we slice our original text by some chunks. Those can be paragraphs, those can be, the most common choice is sentences, but some use some n-grams. And then we form our extractive summary from this sliced text. So we pick some, the most suitable sentences and we form our extractive summary. Abstractive summarization, on the contrary, is when we generate completely new text. So we have to apply some generation models and generate completely new text. And from the very first perspective, it may seem that abstractive summarization looks much more promising because it may generate some texts which are more easily understandable by humans, more intuitive, etc., etc. In some cases it is, but the current level of development of the field still doesn't allow to do that in production, to use abstractive systems in production, because they have some problems which are very hard to track in production, on real data, and they may lead to some problems. So here I listed some of those problems, the most common. So abstractive summarization system, they may start repeating themselves like infinite times. So they may fall in some kind of a loop and start to repeat itself multiple times. And it's actually one of the easiest problems to track with some rules, let's say, on top of the system. They may also make up facts, which is completely very hard to track actually. And they may make up words. They may abruptly end some sentences. They may have problems with coreference and some misleading rephrasing. So yeah, to summarize it, basically abstractive summarization systems, they are good, but they don't give you some control over what you actually outputting. So you don't have full control of the output of the model. And it may lead to some security risks, some biased inference in production. Extractive systems, on the contrary, they will give you like full control of what you're outputting, because all what you are outputting was initially in the text. And the biggest risk here is that you just incorrectly pick the sentence from the text, meaning that it won't be like a good summarization sentence from the text. Looking into extractive text summarization in a nutshell, so this problem mainly consists of 3 steps. So the first one, we have to get some intermediate representation of a text. Basically, I'm talking about some embedding, some numeric representation, which we will use on the modeling stage. The next step is we basically have to score the sentences. And by scoring here, I mean we have to measure how good this sentence is for being a part of a summary. So it means that the sentence with the highest score will be like the best candidate for summary, second best will be second best candidate, etc., etc., etc. So after this second step, what we have just original text, but with reorganized order of sentences. And for doing that second step, actually, we have a lot of method, some simple frequency-driven approaches, latent semantic analysis, graph methods, and bunch of approaches from machine learning, and one of them I will describe further. But it's not the end of a story. We also have to, so imagine that we have like reorganized text, and we have to decide how many sentences, first sentences, best sentences with the highest score, how many of them should we pick for like our summary, which we want to use. So it's selection of some particular number of sentences. And here on this step, I also put avoiding semantic redundancy goal. So essentially, we don't want 2 sentences from our summary would be about the same thing. So we don't want some unnecessary repetition. Okay, let's go further. Now I will describe some metrics that we used. We used this Rouge metric, which is essentially one of the, it's actually the simplest one. Rouge stands for recall-oriented understudy for gisting evaluation. And this metric is very simple, and it's based on some overlapping of words in 2 texts. And we measured overlapping words between a reference summary, which are our ground truth written by human for our data set, and some candidate summary, which we output with our system. So Rouge has 3 parts in it. It's recall, precision, and F1. So here on this 2 example, I showed how to calculate the Rouge precision, recall, and F1 for these 2 sentences. So we have reference summary, the cat was under the bed, and candidate summary, the cat was found under the bed. And with Rouge metric, we want to like estimate how similar this sentences is. And we, for recall, we pick number of overlapping words between these 2 sentences, and we divide it by total number of words in reference summary. And we get 6 divided by 6, 1. For precision part, we also take number of overlapping words, but this time we divide it by number of words in candidate summary. And F1 is just like harmonic mean of those two metrics. It's worth to emphasize that Rouge metrics is far from perfect, because it's we can easily imagine a situation where 2 texts will be very close semantically, but they will have completely other words in them. And in this case, Rouge metric will show you like almost 0, like in these two examples. So we have two sentences, like after taking too many borrows, the company went bankrupt, and the business ceased to exist because of many debts. So they're almost about the same, let's say, but Rouge between them will be almost equal to 0, because the only word which we can, so the only joint word between these 2 sentences is the article the. And also here I wanted to mention that there are a lot of other metrics in the field which are much more sophisticated, and they may even based on some semantics, and they are good for some problems, like BERT score, for instance. We can measure the semantic likeness of two texts between each other. But particularly for our problem, we were good with just using the simplest one, Rouge metric, and this is connected with the nature of our data, and yeah, I will describe it further. So essentially, what we had as a data set. As a data set, we had pretty standard pretty standard setup, sorry. We had texts from customer, from the database, and some of these texts, they were labeled, so the summary were created by humans. They were written partially extractive, partially abstractive. But I would say that they were more extractive than abstractive. But yeah. And we cannot use these human written summaries for training our model because we are doing extractive summarization. And for having this text and human written summary, which I call here reference summary, we had to pick indexes of most suitable sentences from the body text to start to label them first, and then start training. And for that purpose, we use so-called greedy selection algorithm, which I will describe right now how it works. So greedy selection algorithm is a pretty handy technique which is used for labeling your abstractive ground truth summary for picking the most suitable sentences from original text. So imagine that we have a text consisting of 3 sentences. I came into the room, the cat was under the bed, it was hungry and meowed for food. And we have summary which was written by human. The cat was found under the bed, it was hungry. And we want to find some sentences from original text which will be like the best descriptor of this text. And we start with this greedy selection algorithm which has several steps. At the first step, we take all unique words from original text. Second, we take all unique words from each sentence of sorry, on the first step, we take unique words from reference summary. Second step, we take words from each individual step, each individual sentence from the text. And we start iterative process. And on each iteration, we measure Rouge score between our reference summary and each sentence in the body text. And on each iteration, we pick only the sentence which maximizes our Rouge score. So on the first iteration, it will be sentence number 2. And we start like forming our extractive summary. Here, I write down like sentences, but you may also write it down like indexes, because the only thing we need is actually indexes of this sentence. OK, first iteration, we've picked sentence number 2, and we remove it from the text. OK, yeah. And on iteration 2, we start comparing Rouge, but this time Rouge between reference summary, our extractive summary, and we start like looking at the individual sentences from text. And on this iteration, like unique set of words of sentences number 2 and 3 will give us the highest Rouge with reference. And we let's get back. And we pick sentence number 3. And here we have, for instance, criterion that if in reference summary we have only 2 sentences, it means that our extractive summary should also have 2 sentences. Yeah, a couple of additional forms of data set. Our data set was a little bit skewed, meaning that the majority of sentences of that kind of label, after that kind of labeling, they were from the very beginning of a text. So they were first, second, third sentences. And we thought that may be a problem if the new data is coming with different distribution. We decided to somehow fix this problem, and we mixed our data set with Daily Mail data set, which is open data set for summarization problem. And this allowed us to avoid some like overfitting only on first sentences. OK, right now let's look at the model part which we applied. So text summarization, so essentially the name of this slide is the name of a paper that we used as a basis for our solution. on the left slide, on the left part of a slide, you see how usually transformers are used for very common tasks as sequence classification or token classification. So you have embedding, you have some pre-trained transformer encoder like BERT, Roberta, etc., and you feed embeddings into pre-trained encoder, and you get the contextualized embeddings of your tokens. In contextualized embeddings, we already have the information how each token is connected to each other token in the sequence. Then we have some classification layer on top, and we feed these contextualized embeddings into classification layer and get labels. If we need sequence classification, it may be one label per the whole text. If it is token classification, one label per token. In order to use this setup for extractive text summarization, authors of the paper, they did some little modifications. The beginning of the pipeline is the same. So we get these contextualized embeddings of words through pre-trained encoder. And then we have another transformer, which is usually much smaller. It's 1 or 2 layers, and it's randomly initialized. And this one is called sentence level transformer because it outputs us contextualized embedding of sentences. I will describe how it happens on the next slide. After we get this contextualized embedding of sentences, we again use some classification layer, and we get scores for these sentences. Scores, how good this sentence is for being a summary. So essentially, we solved this task as we formulated this task as a training process as binary classification for sentences that we labeled as summary. We used 1, and for all the others we used 0. And the probability of the output, we didn't convert it to some labels in production. We just used this probability, like this score which I described. So here we see how original BERT is working. So in BERT we have several different types of embeddings. We have token embedding, segment embedding, and position embedding. So we sum them up and we feed them into a transformer, and we get this contextualized embedding again. But here it's worth to mention that we also have some special tokens. And it's very important here, special tokens, CLS1, which is placed in the beginning of the whole sequence. So in the classical vanilla BERT, we have CLS token only one in the beginning of the whole text. And we also have some SEP tokens at the end of each sentence. In order to get the contextualized embeddings of sentences, the thing that we want, we did this alteration that we added CLS token in the beginning of each sentence. And in this way, we could use these CLS tokens as aggregated embeddings of the whole sentence after that. So it means that CLS token number 1 aggregates and pulls the information about the first sentence. CLS token number 2 about second sentence, etc., etc., etc. And for the top level transformer, we used only those embeddings CLS embeddings, and we dropped all the others. So after the first transformer, we drop all token embeddings, and we use only CLS embeddings. After that, we feed them to our classification layer, and we score them basically. So this is essentially it regarding the neural network architecture part. And I would like to move further into some custom techniques and heuristics that we've applied. So as you may know, transformers, they have some limitation on the number of tokens that they may process. By default, for the most of them, it's 512 tokens. It may be some problems for if you have long text, and it was a problem for us. And tokens here, it's not words, it's actually some subword representation. So for English language, 512 is about 250 words, which was not enough for us. We required at least double that size. And we end up with 1024. So how we did that? So the main limitation in this, with this regards, is the pre-trained position embedding, which you have in BERT. But we've applied some very simple but very useful trick. We just pick the last element of this embedding and copy pasted it 512 times, and we've end up with double the size of embedding. And this second part we actually fine-tuned on during our summarization task. It's pretty useful technique because I use it on some other projects like later, because it's very often the case that you don't have enough like sequence length for transformers. As I mentioned in the beginning, after ranking, after scoring the sentences, we also have to take care of like limiting the sequence and avoiding semantic redundancy. For semantic redundancy, we used, again, pretty known technique, which is called trigram blocking. It's essentially, we check if there is a trigram overlap between already like summaries and some new candidate sentence. So the sentence with the highest score we always take for granted because we believe our model, and we take it like it's always like the first sentence in our summaries. And each next sentence we check if there is 3-gram overlap between the previous sequence in our summary. And if we meet this condition, we just discard this candidate sentence because we assume that they're telling about the same thing. It's not very accurate actually, but it gives you some like kind of robust approximation. And after we've print semantically with trigram blocking, print our output, we have to limit the length of our sequence, as I told in the beginning. In the majority of cases, people use some fixed number, for instance, 3 sentences. So all the sentences will, all my summaries will be 3 sentence lengths. But we've decided to make it a little bit more flexible. We've fitted some curve on our training data set. And we fit it in the following way. So here on the picture, you see on x-axis, you see length of original text in words. And on y-axis, you see so-called compression ratio and how it's calculated for each particular text on training set. You take the length of original text and you have and you divide it by length of reference summary, and you get this compression ratio. And it means that you may use this number, this curve. It's, I don't know if it's feasible. Yeah, you may use it in production. So imagine that in production we get a text with a length of 400 words, and we may look that for that length, approximately compression ratio will be 15. We divide 400 by 15 and we get something about 26. So 26 is like an optimal length of summary for the text of length 400 words. So let's say like this. And yeah, the last slide about the results. I actually cannot show you the exact work of a model. I mean, I cannot show you the text because of the confidentiality issues, but I may show you some metrics. So here, the first row of a database is the lead 3. It's a baseline, usually we used for summarization tasks. It's first 3 sentences, and sometimes it's very hard to outperform this baseline, but as you may see with all our experiments, so we experimented with different transformer encoders. With all of them, we were able to outperform it. As a final model, eventually we've chosen Electra Small because it's a small model and much more computationally optimized for some production system. Although ExcelNet, for instance, it like performed better, but ExcelNet is like large model, which is very hard to maintain, basically. So yeah, I guess that's it from me. If you have any questions, so feel free to ask. I'll be happy to answer.
Yes, okay. Let's see who has the question. Okay, here's the question. We're getting the microphone.
Thanks. First of all, thanks for the really good insights in your project and the approaches that you took. I was wondering, can you a little bit elaborate why you decided to drop off to abstractive summarization? Because we've done a similar project, and we used the GPT-3 to generate summaries, and then we used humans to annotate the good ones from the bad ones. I mean, it sounds to me like you've dropped abstractive summarization too early. So can you tell me, am I having a good impression, or did you try to push the abstractive summarization further down the line?
Thank you. It's a good question. Actually, we've done quite a lot of experiments with abstractive systems. We didn't try GPT-3 because at that time it was not even, it didn't exist at that time. We've tried with Prophet and several other like abstractive approaches. And we've basically met these problems, some of them which I've described, like imaginary facts, hallucinations. And we've decided that it's like more robust and more reliable to use extractive ones.
Yeah, I mean, the idea is use GPT-3 to generate summaries, use humans to go through them, and then create completely new BERT or whatever summarization model.
Yeah, that's a way to go.
And also, you said that you had 2 little tokens. Have you tried using something like Longformer?
For that project, we didn't try, but yeah, I'm aware that there are other approaches to handle like long input. We just applied this like because it was easier for us. Yeah, like as usual. Yeah. Actually, in future, I think that we will think more thoroughly about moving to some abstractive solutions.
Thanks.
Okay, thank you.
Thank you. Any other questions? Here, 2 questions here. Okay, the first one. No, you can start.
Yeah, thank you. So yeah, I would also like to thank you for the presentation. I'm not fully. I just want to clarify like my understanding, because did you use transfer learning like for your encoder models at the end? So you had your data set. Did you use some pre-trained models for your source data, or you use some basis and then fine-tune it like for this table? Yes. Yeah,
sure. So we used some. We did experiments with several pre-trained models that I listed here, and they were trained on like big data sets, and we fine-tuned it on our task. Yeah.
Okay. And was it like also still time-consuming depending on your data size, or it was fine? Like, did you need to use multiple GPUs for that, or?
No, actually, we didn't use multi-GPUs. It's if it's some small model, you can train it on some single GPU. So it actually was satisfactory for us. And small models, they are pretty compact. You may use them in production on some single CPUs even. So
okay,
optimize it.
Thank you very much.
Another question there.
Thank you so much for this amazing representation. My question is, what is the threshold which we are using for this particular matrix in order to like check the accuracy for the models?
Good question. We didn't have any like threshold. So essentially, when we've come to this project, there were any annotation for this system. So user were struggling with always asking for some access. We've did this evaluation of baseline, and we saw that our systems are performing much better. And after that, we've got only like positive reports from the users. So we didn't use any threshold here. So we just picked the best that we had.
Got it. So upon the same, I have another question, and I guess this is probably for all the data scientists present over here. So when we do topic modeling, so this question is again around the accuracy metrics only for NLP. When we do topic modeling, we use some kind of metrics like coherence score or perplexity and all those things. But when I go and sell my model to my client, how can I tell them this is the best topic models, the best mapping for your text, which we have done, the best evaluated topics, which we have derived from our text. So how can I exactly derive that? Because for me, a coherence score of 0.6 or 0.7 for all us, for all the data scientists, it's a decent score for a topic model. But how does we convey this to a client that this is a good model and it'll work fine and it'll give you a good result? I can show a couple of results to them that this is how we are validating. But let's say I have 5 lakh of rows of data. How can I robustly say that this is a perfect topic model which you can use and apply to your any voice quotes or anything like that? So
Yeah, well, it's actually a quite complicated question. It always depends on the client, on the setup, that on the business requirements, etc. For this particular thing, we had like a round of manual validation of our generative summary. So we had some like experts from clients
like
side.
domain expertise, yeah.
Yeah, and they validated that it's actually good to use. Of course, not on the whole like data, but on some subset.
All right. Thank you so much. Yeah.
Okay. Well, we're stepping into the next presentation
Thank
now.
you.
Anton, thank you.
Thank you.
Anton Guldinskii.